So we're at day 5, lesson 5 for chapter 3. Today we're going to take a look at power. A bit of a shorter lesson compared to the first few lessons of the chapter, mostly because it's review from Physics 11. So power is just the speed at which you can accomplish some work, or the speed at which you can move energy around. It's actually a calculus thing, I guess, called a derivative, but we can get at it just by taking the work or the energy change involved in the story and dividing by time. Or at least that was our plan from Physics 11. And so if power is just this work divided by time, you could rearrange it and say, oh, okay, well then the energy or the work involved is power multiplied by time. Okay, a very common way to rearrange things. The units are named after James Watt, so it's going to be a capital W when we talk about the power. One thing to be careful about, the abbreviation for the unit for power is also the abbreviation for the quantity work, but they're totally different things. One's a unit and one's a quantity, so we should be okay there. Here's our first of 4 examples. We're going to do this one twice, though. It says, how long will it take a 300 watt motor to lift up a 670 kilogram container pretty far up, 18 meters vertically? Not the most powerful motor. It's going to take this thing a little bit of time. Now, I want to show you this one twice, just to show you a neat little way to organize things. In Physics 11, we probably would have said, oh, well, the powerful motor is going to do some MGH, and it's going to take some time. Maybe it might be nice to rearrange it and say the energy we get from the motor, the potential energy, would just be its power times its time. And we might have just kind of jumped in right here. And there's nothing wrong with this, right? You can say, yep, 300 watts, I'm looking for time, and it needs to go and do the MGH. And it absolutely gives you the right answer. Okay, 394 seconds. Somewhere between 6 and 7 minutes, right, for it to do this lift. And that's great. It's done. But here's a different way to look at this. Okay, so maybe just put a little line underneath that solution. And here's another plan. I want to show you that this can be consistent with what we've been doing with conservation of energy. So often we look at the different physics lessons and say, oh yeah, they're just unrelated things. Now we're doing this. But you kind of want to look at the big picture and see how things tie together. So we've got this conservation of energy equation, and it's perfectly fair for you to look at it and say, yeah, power doesn't go in there. There's no place for it. Well, there kind of is. This motor is going to do some work, and I get it. You might say, well, work is force times distance. There's no power. Yeah, but that 300 watts tells you that it can do work 300 joules every second. So another option for thinking about this work in from the motor, yes, okay, it's force times distance, but you can also take that force times distance, you can swap it out and say, hey, it is power times time. So yeah, I'm going to use this big organizing equation because I like the fact that I can say, oh, the container wasn't up high at the beginning and scratch off the first MGH. It wasn't going fast at the beginning and scratch off the first kinetic energy. And then the work in, if I choose to, I could say, power times time. And then it does have some MGH in the end. It doesn't need to have any speed in the end, and there's no talk about it rubbing. So big picture, I can actually use this as an organizer. Now, of course, by the time you get to here, it's the exact same solution we have at the top of the page. It's identical, but it just gives you another way to think about how you're jumping into this problem, that really it is conservation of energy. The energy's coming from that motor. This is just allowing you a different way to kind of manage all of those calculations. Okay, let's just do 3 more. Here's the next one. 15,000 kilogram airplane is at rest on the end of a runway, just waiting to take off, just sitting there about to go. 4 minutes later, you find the airplane way up in the air. It's 3,000 meters up, and it's going 140 meters per second. And we're being asked, well, what kind of power would you need from your engines to get that all done in just 4 minutes? Right? So the speed at which you can accomplish this is going to help us decide what that power would be. The reason why they say minimum power is we're probably going to end up underestimating the power. It's probably going to be more than what we think because air friction is not going to be included in our calculations, and there would be some heat from that. And so you would need definitely a little bit more energy than what we're going to go with, but at least we can get kind of a baseline. So it looks to me like we're going to have to lift the plane up, and we're going to have to make it go fast. And I'm going to ignore this. I'm going to say, yeah, let's pretend there's really no heat. The plane starts off on the ground, so the potential energy initially is 0, and it starts at no speed, starts from rest. And here's that work in. Okay, so I can think about that as being just power times time, trying to get this airplane up into the air. And so I like this idea of continuing to use last day's equation where it works really nicely. I can't cancel the m's. I'd have to change the time from 4 minutes to 240 seconds, and then it all falls apart pretty nicely. So again, just an option to think about that conservation of energy equation as an organizer for the work that you're doing here. Okay, it ends up being really big, 2.45 million watts. If you wanted to, you could say 2.45 megawatts, right? Kind of sounds cool. It's an option. You don't have to, but you could do that if you wanted to. All right, second to last one. 250 watt motor is pushing a 120 kilogram crate. Maybe it's like in a warehouse. We've got like a little motorized cart shoving it. And we're going at 4.5 meters per second across a rough floor. And we're going to try to figure out how sticky that floor is. What's the mu value? You don't have to have a free body diagram. I'm not doing this the old chapter 1 way with kinematics and dynamics, although you certainly could, right? You could think about the acceleration being 0 and what's it going to take to get a net force of 0. But actually, I just want to go at this right from the point of view of just power and energy. We're going to go at a constant speed, 4.5 meters per second. So it's looking like the applied force from the motor will have to be exactly the same size as the friction force. That can be helpful in my calculations. Okay, power, that 250 watts, is the work it does divided by time. What's interesting is it doesn't say what time is going to be, right? Like how long does this experiment run for? And work would be force times distance. I don't know how far we go, right? How many meters do you go and how long do you run the experiment for? Now, a lot of people like to do this. They say, well, can't I just imagine it goes for 1 second? And if we go for 1 second at 4.5 meters per second, my displacement would be 4.5 meters and my time would be 1 second. And I would agree that that's a perfectly reasonable way to get to the right answer. There's a slightly more refined way. Instead of saying that, you could say, well, look at this d divided by t. In stories where they say it's a constant speed, whenever you see d divided by t, that's actually the velocity. So for constant speed stories, power is actually force times the speed that you're pushing this thing. I'm going to use that, right? It's just a little bit more elegant than saying, oh, well, 1 second, or other people say, oh, 10 seconds would be 45 meters. Yeah, how about we just go force times velocity? Now, finding that applied force, right? Well, thinking about the applied force from the motor, it's the same size as the friction force. They're different things, but they're the same size. So I know this is technically the applied force from the motor, but it's got to equal the friction. And if we're not on a ramp, then I can just go mu mg. And again, this, you can just write that as a v if you want. Write that d over t. There we go. We'll explicitly do that. So, calculations, they go pretty simple now. 250 is our wattage, looking for the mu value, and then the m and the g and the v. So the key thing with this one is that if you ever see a d divided by a t and it's constant motion, you can say, well, that's just going to be the velocity, the constant velocity that we're going at. And it doesn't look like this floor is very sticky, right? It's a pretty small mu value. Final question. Let's take the one we just did and let's make it more interesting. Let's go on a hill. Let's go up a big ramp. So how much power is necessary to drive a big like logging truck or something like that up a steep hill? It's pretty steep. We're going to go at a steady speed, just brutally slow. Oh, and there is some friction force, but don't worry, I've already calculated it for you. It's 4,600 newtons. But you just need to be aware that it's there. So I need a little picture of my truck going up the hill. I've got my mg going straight down, and I'm going to break that up into a crush and a slide. The normal force would just equal the crushing part of gravity. There's definitely an applied force from the motor. It's going to actually be tied, but tied with both friction and the slippery part of gravity, right? We don't want any winners there because we want a nice steady speed. And the friction, I'm just going to offer that to you, 4,600 newtons. So some key things to pick up on is that tie between the applied force and the two backward forces, the friction and the slippery part of gravity. The other thing we're going to work with is how we can go with that constant velocity again and say, oh, well, that'll be d divided by t. So I have that same issue. The power is the work done by that motor divided by the time, and there it is again, d over t. I can just call that a velocity, right? So I'm not intimidated by that d over t at all. I do know that the applied force from this motor will have to be tied with both friction and the slippery part of the hill. But yeah, that should work pretty nicely. Plug and play at this point. They're asking us for the power. Perfect. The power is already isolated over there on the left, so we can just throw the values in. So you can see me calculating the mg sine theta value, right? 3,200 kilograms, 9.8 sine of 18, and then adding on friction to see how big this applied force should be. This division by 3.6 was me dealing with the kilometers an hour in order to work with meters per second. And I've got the right answer. It's 2.11 10 to the 5 watts, or some people might say 211 kilowatts if you imagine the decimal kind of being like right before this 4. It's 211,000 watts, right, for this motor. But most people probably wouldn't say that for a truck motor. They probably wouldn't say like, oh yeah, it's 211,000 watts. They'd probably talk about horsepower. So just one last little issue here. Some other units. 1 horsepower, if people ever talk about it, I think one of the homework practice ones does. 1 horsepower is 750 watts. So if they say, oh yeah, it's a 100 horsepower motor, you can just multiply by 750, find out how many watts you've got, and then you're good to go. And that's where we're going to wrap up this lesson, a little bit shorter than the last ones.